Hi, my name is Tatum Hardy, and this is Lab 4. In this lab, we'll be predicting the behaviors of circuits containing resistors in series and parallel using multimeters to measure the actual values of the conventional current and potential differences in the circuits. We'll also be examining the behavior of both ohmic and non-ohmic resistors and capacitors using the principles of energy conservation and current conservation. The sections of this lab include, in Part 1, ammeter results, voltmeter results, electric potential versus positions around the circuit, and resistance of components. Part 2 is RC circuits, and finally we have the conclusions. The results for Part 1 are as follows, and the results for Part 2 are as follows. When we create a simple series circuit, much like the one on the top left-hand corner image, we are able to use the loop rule and the node rule to predict the amperage values of the current. The value of current through each of the resistors is 0.02041 amps according to our predictions, and these values are the same due to the node rule. When the circuit is actually set up in an experiment setting, we get that our predictions are correct. And even if the ammeter on the bottom is reversed, the current remains the same. If we are to replace one of the ammeters with a voltmeter, no current runs through the circuit. This is because an ideal voltmeter has no current flowing through it. This is achieved by having maximum resistance so that the current flows entirely across the original path of the circuit. Since the voltmeter simply replaced the ammeter and was not attached across one of the circuit's components, no current is flowing through the circuit. When measuring the voltage drops across each component of the circuit, as shown in the image to the left, we get that each of the voltage drops are as follows. The voltage drop across the battery is 3 volts, which is positive based on how we orient our voltmeter. Our voltage drop across each of our wires is 0 volts because they are ideal for this lab. Our voltage drop across the 47 ohm resistor is negative 0.959 volts, and the voltage drop across the 100 ohm resistor is negative 2.041 volts. The voltage drop across the ammeter is also 0 volts because it is ideal. Notice that the summation of all of these values is equal to 0. The potential differences across each section of the circuit were recorded using the experiment software. If the voltmeter was oriented in the same positioning in each section as it was in my experiment, the sum of the potential differences was 0 volts. Graph the electric potential versus the position around the circuit. We can see that the circuit starts at 0 volts, and as it crosses both the batteries, it gradually increases by positive 3 volts. The 47 ohm resistor results in a slight negative slope to have the overall potential difference of the circuit become 2.04 volts, and the 100 ohm resistor is much steeper and results in the circuit becoming 0 volts again. This larger gradient of potential across the 100 ohm resistor is due to the electric field being large across the 100 ohm resistor. Using Ohm's law, we are able to find that the resistance across the 47 ohm resistor is 46.987 ohms. The resistance across the wires are 0 ohms. The resistance across the 100 ohm resistor is 100 ohms, and the resistance across the ammeter is 0 ohms. If an ammeter was to be attached in parallel, the value of the current would change. This is because an ammeter has ideally 0 resistance. Essentially, this means that you are just creating a new branch or a new path within the circuit, which creates a different flow of electrons and therefore a different value for current. For part 2 of the experiment, we were to create an RC circuit like the one as shown in the image on the left. A few seconds after the circuit is connected, the capacitor starts to build charge, but the light is still shining. The light becomes dimmer as the capacitor builds more and more charge. Once the capacitor is fully charged, the light goes out. The time to charge for a 10 ohm resistor is 17.013 seconds. If we were to remove the battery and the circuit is just the light and now the charged capacitor, the light starts as a fully illuminated bulb and slowly becomes deluminated. The time to discharge is 16.962 seconds. The same circuit is repeated for a 20 ohm resistor bulb, and the time to charge is 30.365 seconds, and the time to discharge is 31.114 seconds. Using energy conservation for the circuit, we can find the time to bit voltage across a discharging capacitor. The relationship for the change in voltage is the initial voltage times e to the negative t over RC, or over time constant. We change the energy conservation equation to become a function of time, and then make this function of time a logarithmic relationship. We find that the natural log of delta V over delta V naught versus time yields a straight line with a slope of -1 over the time constant. As shown in the graph below, the discharging of a circuit is represented by the black dotted line, and the charging of a circuit is represented by the solid red line. When we plot the charging of a capacitor as the logarithmic function dictates of the circuit in the image to the left, we find that the slope is indeed negative 0.167, and it produces a very linear, straight negative line. In conclusion, if we were to use an actual ammeter, that would not be ideal. It would have resistance. This means that the ammeter would have voltage running across it. The voltage across the ammeter would cause a redistribution of the voltage drops across each of the components in the circuit. Also, if a battery was used to charge a real capacitor with no resistor in the circuit, it would instantly charge the capacitor, making the function a vertical line. This prediction would not happen in actuality because both a real battery and a real capacitor would have internal resistance. Thank you. This was my lab number 4.